A very important idea in computer science, of course, is the idea of an algorithm. If we want a definition, an algorithm is a finite sequence of precise instructions for performing a computation or solving a problem. And yeah, these instructions have to be precise enough that we can give them to a machine, to a computer. But we could be doing them by hand. For example, we're used to the quadratic formula. And so if you start with a quadratic equation, you can solve it. It's just a simple step-by-step algorithm using the quadratic formula. All right, so that's what we're looking at today. Okay, so yeah, a very simple example to begin with. Let's look at an algorithm to find the biggest integer in a finite set. Okay, so important ideas for algorithms. Yeah, the idea of the input and the output. All right, so a bit like a function. So algorithms, they're expecting some specific kind of input. In this case, it'll be a list of integers. And then the output, so what the algorithm produces, what it returns, is supposed to be the biggest number in that input list. So in this case, pretty easy to see the biggest number here is 13. So that should be what our algorithm produces. Could our algorithm just be look for the maximum integer? No, so that's not precise enough. Yeah, if the input was much bigger, say a list of 1,000 integers, then yeah, how exactly is the machine supposed to look for the maximum? All right, so yeah, we want a precise steps. Well, here's one way. Yeah, there are different ways, but a simple way is step 1. Set the temporary maximum equal to the first integer in the input list. Okay, so if we were starting with this list, our temporary maximum would be 9. Step 2, compare the temporary maximum with the next integer in the list. If the next integer is bigger, then make it the new temporary maximum. Okay, so think of variables, variables storing different numbers. So at the beginning, this temporary maximum variable is storing the 9, but then comparing the 9 with the 13, yeah, the 13 is bigger, so now we're going to store 13 in that temporary maximum. Step 3, repeat that last step. Okay, so 13 is the temporary maximum. Compare it with the next number, 2. Well, 2 is not any bigger, so we'll keep that temporary maximum. Okay, then compare with 6, then compare with 11. Okay, so keep going till you've got to the end of the list. All right, when you get to the end of the list, then whatever number is stored in the temporary maximum, that's going to be the output, and that'll be the maximum of the input list. So yeah, this is an important idea here, this idea of a loop. So our algorithm is repeating a step. Okay, so we describe these steps just in words, just in English. How could we code them for a machine? Well, yeah, there are different programming languages like C or C++, Python, Java, which are all slightly different, or maybe more than slightly different. But instead of working with a specific language, in this course we work with pseudocode, which is easier to understand, less technical, but it's easy to convert. So if you know these other languages like Python, then it's easy to convert pseudocode into Python. Okay, so let's see what our four-step algorithm, what does it look like in pseudocode? So here's the pseudocode version. All right, so we have a procedure, so we always start like this, procedure. Here's the name of the procedure. And we'll call it max. And the next thing in parentheses is the input that max is expecting. So the input is a list of integers. Okay, so we're giving the type integers. And we're listing them like this, so A1, A2, up to A subscript n. All right, so that's telling us that our list has n elements. All right, so our procedures will always have the same format, so the name of the procedure and then the input. Okay, so what happens next? Okay, we're using, probably confusing, but for our temporary maximum, we're using the variable max. Okay, so this variable is going to store the biggest integer found so far. And in our steps, we first let max be the first integer in the list, a sub 1. Colon equals, what's that about? So that's assignment. So we're assigning the value of whatever A1 is to max. All right, so this, very common. We use equals for when we're comparing two things, but assignment when we're letting a variable, giving it an assigned value. Okay, so now max is storing the first number in the list. Okay, here we have a for loop, so this is one type of loop construction. And there's a variable I. So the for loop is letting I go from 2 to n. Okay, so I starts off equal to 2, and then it keeps repeating this piece as I goes from 2, 3, 4 up to n. Okay, remember our list has n elements. Alright, so what's this repeating step? Well, it's just this, steps 2 and the repeating it. So step 2 is compare the temporary maximum with the next integer in the list. If the next integer is bigger, make it the new temporary maximum. Alright, so that whole thing is happening here in this line. So if the next integer in the list, that's a sub I, is bigger than the temporary maximum, then we're going to assign, we're going to let that temporary maximum be that new number, a sub I. Okay, so we keep repeating this step until we get to the end of the list. So the last step here is if the temporary maximum is less than a sub n, the last number in the list, then let the maximum be that number a sub n. But if the max is bigger than or equal to that last number, then don't change it. Yeah, I should say we have another construction here. So if this if-then construction, all right, so this piece is a condition. It's true or false. So if this condition is true, then do this. But if the condition is false, then don't do this instruction. All right. So this if-then idea. So if the condition is true, then do this part. But if it's false, then don't do this part. All right, so simple conditionals. Yes, it's explained here again. And yeah, finally return. So the return gives the output, and the output is whatever number is stored in max. That's the biggest number the procedure is found in the list. All right, so that's the procedure written in pseudocode. Let's see an example. Show all the steps used by this procedure if you give it this input, 9, 13, 2, 6, 11. All right, so first our input gets stored like this. So A1 is 9, A2 13, up to A5 is the last number. So N is 5 numbers in the list. Then on the second line, so the max is assigned A1. So now max is storing the number 9. Then we start the for loop. So first I is equal to 2. Okay, so I starts off equal to 2. Then we check this conditional. So it's saying if max is strictly less than A2, then do this. Well, max is 9, A2 is 13. This condition is true, so we do carry this out. So now max is assigned 13 from A2. All right, we're still in the loop. Next, I is equal to 3. Check the condition. 13 strictly less than 2. Well, that's false. Okay, so a sub I is now a sub 3, and that's 2. Okay, since this is false, then we don't change max. All right, the loop loops to I equals 4, and this is similar, so 13 strictly less than 6 is also false, so nothing changes. And when I is 5, 13 strictly less than 11, it's closer, but it's still false, so we don't change max. Okay, after 5, that's the end of the loop. So we break out of this for loop, go to the next line, and we just return whatever's stored in max. All right, so max is 13. So that's the output. All right, so that, yeah, this is the key step, yeah, this comparison. So if the maximum that you've currently found is less than the next number, then change your maximum to that bigger number. And of course this procedure would work with a much longer list if it was, say, 1,000,000 integers. Of course, they don't even have to be integers, they could be any real numbers. This simple procedure would work. Yeah, so it's so simple yet it's clear that the algorithm's always going to do what it's supposed to, return the maximum. Of course, yeah, if you try to give it some kind of infinite lists, then the procedure would, maybe try to keep going forever, so that wouldn't work. But if you give it a finite list, then the procedure definitely finishes. So it's finite and effective, yet there's no chance that it can keep running forever, which is it's not going to crash, right? It's just stepping from 2 to this finite number n, so what could go wrong? Yeah, so let's take a look in the book. Yeah, here's the definition I copied. Yeah, the kind of the strange word algorithm, it comes from the name of this mathematician, Al-Khwarizmi. Al-Khwarizmi. Here he is, yeah. Originally from Uzbekistan. So yeah, way back in the 9th century, he was working on algorithms. He was also doing algebra. Yeah, the word algebra comes from the title of his book, Algebra. Okay, so here's that maximum procedure. And so yes, the properties of algorithms, yeah, we want a specified input, and the output should be clearly specified, yeah, that the solution to the problem or the calculation. The steps of the algorithm must be defined precisely, so yeah, definiteness. Yeah, it should work correctly. Finite, so we don't want it looping forever. Effective, and it should work in general for any kind of input, the most general kind of input. Yeah, also in the book, if you look in Appendix 3 at the back, there's more information about pseudocode, the details of this pseudocode. Yes, so we'll see more examples. But yeah, so if you're writing a pseudocode algorithm or procedure, then yeah, it should have a format similar to this. Okay, so it's fairly precise. All right, so let's look at some slightly more sophisticated algorithms. Well, not much more. Searching. So suppose you're looking up a word in an online dictionary. Well, you just type it in, but how does the system find the word that you're looking for and then display its meaning? All right, so this online dictionary, it's storing all the words, all its words in order from, yeah, starting with, I guess, A would be the first word, to maybe this is the last word. All right, so A to Z, this lexicographic order. Instead of words, we could be searching a list of integers. Again, maybe that's slightly easier. Okay, so we'd like to know where in the list a particular integer is, or maybe figure out if it's not in the list. Okay, so searching, in this context, searching just means searching for something particular in a list. Okay, so in our first case here, let's assume our integers are not in order, but we are assuming they're all different. For example, we could have a list like this, so 6 different integers. If we're searching for the number 11, then we see, just by looking, 11 is the third number in the list. Okay, so if we're searching for 11, then the output should be 3. If we search for 8, I don't see it. It's not in the list, so to signify this, we could output 0. Okay, so 0 means not in the list. So not there. Alright, so our algorithm we'll use for this is called linear search. And it's similar to the max procedure, so it just steps through the list. Procedure, here's the name of the procedure, linear search. Here's the input. So this is what goes in. So it's expecting, so the first thing is it's expecting an integer x. This is what it'll be searching for. So searching for this x. And then the second thing is a list of integers, distinct integers, a1, a2 up to an. So like before, a list of n integers. So it starts off, so I is assigned the number 1. We have a new type of loop here, a while loop. Okay, so the idea of a while loop is there's a condition, and while this condition remains true, it keeps doing whatever this is. Okay, so while I is less than or equal to n, so while we're still in the list, and x is not equal to ai, remember x is what we're searching for. Okay, so this means that the ith number in the list is not what we're looking for. So while these conditions are both true, then just increase I by 1. Yeah, so this is a common assignment. Yeah, this means we're assigning I the number, the current value of I plus 1. Yeah, so this would look strange if it was just an equal to, but it makes sense as an assignment. So it just means increase. So whatever is stored at I, increase that number by 1. Okay, so we need that for the while loop to get to the next number. Alright, so this while loop, so two things, there are two ways to break out of the loop. Either I becomes bigger than n. Okay, so we've got to the end of the list. The other way this can be false is if x is equal to a sub I. That means we've found the number we're looking for. Alright, so if we get to the end of the list, or we find the number we're looking for, then this becomes false, and we break out of the loop and get to this next step. Yeah, so here we're trying to figure out what happened. So if I is less than or equal to n, well, that means that this is true, so then this must have become false, so that means we did find the number we were looking for in location I, so it was a sub I was the number we were looking for. Okay, so if this is true, then let the location be I. Else, and so if this is not true, then do this. let the location be 0. Okay, so if this is false, then I is bigger than n. So we've gone past the end of the list. We haven't found the integer we were looking for, so it's not in the list. So we'll return 0. And so the last line is return that location number. Again, it tells you if the output is 0, then the number we were looking for is not in the list. If it's a positive integer, then that's the location of the number. Alright, so we used a while loop. And this kind of extension of the if-then construction, if-then-else. So the condition P, it's true or false. If P is true, then do this. If P is false, then do this. So P has to be true or false, so one of these is going to happen. So that's an important programming construction. Alright, so I hope that makes sense. So so just searching. Okay, so this procedure just steps through the list until it finds what it's looking for, or else gets to the end of the list and doesn't find the number. Alright, so let's look at a slightly different problem. So now we have a list of integers that are distinct, but also now they're in increasing order. So the numbers are listed from smallest to biggest. Okay, now if you're searching an ordered list, then that should be much easier. If you've ever actually picked up a physical paper dictionary and look for a word, you don't start with the first word, then the second word, then the third word. No, you'd maybe open the dictionary in the middle, see, okay, is the word you're looking for going to be before that or later than that? Alright, so so it's much easier to search ordered lists. And so at each step you could kind of break the list into two parts. Alright, and depending on what you're looking for, it's going to be in the first part or the second part. And that's how a binary search algorithm works. Binary, so you're breaking lists into two parts. The way it works, the procedure keeps narrowing the search to say between the ith and jth numbers in the list. Alright, so if you've narrowed down the search to this range, a sub I plus 1, ... up to a sub j, okay, so if you know that if the number's in the list, it has to be here. Well, now you want to break this into two. Okay, so find the middle number, a sub m, and then you're going to compare the number you're looking for with a sub m to see, okay, do I need the first part? Or if the number's bigger, do I need the second part? So if the number you're looking for is bigger than this middle number, and you know that it can't be in the first part, so now you can ignore that, and you've made the problem easier. You've got rid of a bunch of numbers in the list, and then you can search here, and then repeat that procedure. Yeah, it's a very common idea in algorithms, is to sort of make the problem easier by kind of dividing the problem into two parts, and then look at each part. There's one issue here. So what is the middle number? So what's the index? What's the middle index? M. Well, if you have an odd number or an even number of numbers in the list, there might not be an actual middle number, but if we take the average of I and j, so I plus j over 2, and then if you remember the floor function, so we want the greatest integer that's less than or equal to this number, so this could be a fraction. Alright, so we're getting the middle index. We can't just take the average, we need an integer, so use the floor function to get an integer. Once you have that middle number, then compare it with the number you're searching for, x. If x is bigger or smaller, then you can adjust the I and j. Alright, so if x is bigger than this middle number, then move I up to m, or maybe m plus 1. If x is less than this middle number, then move j down to m. Okay, so we restrict the search range. Okay, then keep doing that until I is equal to j. So you just got it down to just a single number. Okay, hopefully that number is the one you're searching for, but if it's not, that means the number was not in the list. Okay, so this is more complicated. More things here. We have to keep track of I and j, so this gives us the search range. Call this procedure binary search. The same input as before, except now our list is increasing. Assign I to be 1 and j to be n. Okay, that's the full list range. And we have a more complicated while loop. And just the way this is set up, we can see this is the while loop because it's indented here. It's kind of tabbed in. Okay, so when this while loop is finished, then we get to this if line is next. Okay, so this part here indented, that's what gets repeated in the while loop. Well, here's the condition that has to stay true to stay in the loop. I has to be strictly less than j. Okay, so if I is equal to j, then you've narrowed the search down to one number. But if I is less than j, then let m be this middle number between I and j. If the number we're looking for is greater than that middle a sub m, then move up the lower bound to m plus 1. Otherwise, so if x is less than or equal to that middle number, then move the upper bound j down to m. Alright, so that narrows the search. Okay, and then go back to this condition, check that I is still less than j. If it is, then repeat. Okay, so divide the search range in two again. So keep dividing until I is equal to j. Then we come out of that while loop. And so now all that's left to do is check, so is the number that we're looking for equal to that a sub I, that possibility? If it is, then we've found the number x at location I. But if it's not equal, then we're out of luck. X is not in the list, so we'll return 0 like before. And finally, return that location number. So that's our binary search. And quickly, just to see it in action. So just this list, n equal 4 elements in the list. And let's say we're searching for the number 6. Okay, so x equals 6, that's what we're looking for. We have A1, A2, A3, A4. Our initial setup has I equal to 1 and j equal to n. Alright, so all this part is called the setup, or the initialization. Okay, then we get going in the while loop. So 1 is less than 4, so we start doing this. Calculate m. Okay, so 1 plus 4 is 5. 5 divided by 2 is 2.5. And the floor of that, so going down to the next integer, that's 2. And then our conditional. Alright, so x is 6, m is 2, so a sub m, a sub 2 is 3. So if x is greater than a sub m, so if 6 is greater than 3, okay, that's true, so do this first piece. Assign I the value m plus 1. M is 2, so I becomes 3. Yeah, this was true, so we don't do this. Alright, so you see what happens. So okay, so we broke the list in two. This was our middle number. And then we compared this to x. It was less than x. or x was greater than it. So that tells us that the number we're looking for has to be in the top half of the list. So we're moving I from 1 up to 3. Alright, so now we just have to search in this range from I equals 3, the third element, to j equals 4, the fourth element. Okay, so that's progress. Now go back to the start of the while loop. Yeah, I is still less than j, 3 is less than 4. So continue. M is now 7 over 2, that's 3.5. The floor of that is 3. Comparing x with a sub m, a sub 3. Well, now x greater than a sub m is false. 6 is not strictly greater than 6. Okay, so that's false, so we don't do the first one, we do the second one. J becomes 3. Alright, so the I stays at 3, but the j comes down to 3. Okay, going back to the while loop. Yeah, now the condition becomes false, so we break out of the while loop. Alright, so we finished the while loop. Now we get to this conditional. Now we see, we have found, so x is equal to a sub 3. So let the location be 3. Good, we found it. And return that location. And so the output is 3. Alright. Yeah, it's a good thing it's a machine doing this, hopefully. But we can step through it, at least for small lists. So the number we were searching for, 6, is in the list. It's the third number in the list. Alright, so that's our introduction to algorithms. We'll continue this section in the next time.